Every second, your brain fires billions of electrical signals. These patterns of activity encode everything you experience, your memories, choices, and how you perceive the world. For most of history, neuroscience was limited to observing behavior or studying the brain's physical structure. We could see how a person acted, but the actual process of thinking remained inaccessible. Modern imaging is beginning to bridge that gap. We are moving from studying the biological container of the mind to interpreting the information moving through it. The primary tool for this work is functional MRI, or fMRI. It functions by tracking changes in blood flow throughout the brain, rather than reading thoughts as text on a screen. When a brain region becomes active, it uses more oxygen. The fMRI detects these shifts, creating a visual map of neural activity. But these maps are complex. Without correlating blood flow to specific mental states, the data remains biological signals without clear meaning. The current goal for researchers is to create a reliable translation layer, identifying exactly which patterns of oxygen usage correspond to the images a person sees or the decisions they make. Looking at a face activates the fusiform face area, while a landscape triggers a different network. Machine learning models analyze thousands of scans to identify rules, learning to associate specific visual stimuli with corresponding neural signatures. Researchers can now take a new MRI scan and use these models to reconstruct an approximation of what the subject is seeing, identifying a person, a specific object, or a geometric shape. This is possible because the brain represents experiences as a network of distinct features, such as color, motion, and edges. By capturing the signals for these individual features, we can reverse engineer the overall experience. These experiments demonstrate that subjective visual experiences leave a consistent, objective trace that can be measured and translated into data. This mapping goes beyond external sight. It also applies to internal states, like the act of retrieving a memory or simulating a plan for the future. Abstract mental tasks have their own identifiable signatures. Solving a math problem, for instance, produces a different neural arrangement than making a social judgment. Neural patterns can predict a choice before conscious awareness. This timeline shows the brain preparing the decision early. It suggests thinking is layered, organizing information in subconscious layers before the final result bubbles up to our awareness. While we experience our thoughts as a single, instantaneous inner voice, the biological reality is a complex system working ahead of our conscious experience. What we perceive as a spontaneous thought is often the final output of a layered predictive process happening beneath the surface. This technology is already being used to assist patients who are completely unresponsive due to paralysis or severe injury. By asking patients to imagine specific physical tasks, like playing tennis, doctors trigger distinct, readable patterns, even if the patient cannot move. These action-based neural patterns serve as proxies for communication. A specific imagined action can represent a yes, while a different mental task represents a no. By detecting these physical traces of thought, brain imaging provides a way for people trapped in unresponsive bodies to share information with the outside world. As the ability to decode these patterns improves, it raises important questions regarding the privacy of our internal states and where medical utility ends and personal intrusion begins. The technology currently requires massive stationary equipment and cannot capture a word-for-word inner monologue. It maps broad patterns rather than specific, complex ideas. We are like listeners standing outside a concert hall. We can sense the rhythm, the intensity, and the structure of the music inside, but we aren't yet able to read the sheet music. What we have confirmed is that every memory and decision exists as a physical, dynamic trace within the brain's network. We are beginning to map the physical generation of these patterns, the very signals that define what it means to be you.